Here is another example of what we can do here using this little electronic whiteboard program. So let me know if you like this, and I could certainly institute this a little bit more. It might be a little bit easier to see, definitely easier to mark up something from the lecture slides. Another thing I think that I forgot to mention in any other video is I always post PowerPoint lectures that are sometimes really helpful for your learning, but I don't often like to use them just because it gets a little bit boring, certainly for me, and I can't imagine if I'm bored that you guys aren't bored either. So anyway, what I did with this particular one is I just kind of picked out just an example of an organic compound that's out there. And what we're going to do is we're going to talk about it a little bit in terms of the like things you should know about the structure, and also kind of different ways that I can figure out how many lone pairs of electrons around here, and also how many times different types of atoms like to bond. We've already talked about the fact that carbon likes to bond 4 times, but it turns out that if we kind of take a look at nitrogen, let's say, this guy right here, you'll notice that nitrogen likes to bond 3 different times. Keep in mind that it still has a satisfied octet, because what's often not shown in these is the fact that there is a lone pair of electrons, and let's see if I can actually show this correctly. A lone pair of electrons are present on this. Oops, it didn't work. Let's try that one more time. So obviously I meant to put those directly on nitrogen. That looks a little bit silly. Maybe I should have made the paste a little bit bigger. But the idea is that that nitrogen right there still definitely sees its full octet of electrons. You'll notice that particular nitrogen has got a total of 8 electrons around it. And so one of the things that I'd like you to know, and I'll make a note of it over here, is that nitrogen bonds 3 times, or it likes to bond 3 times, but it can bond 2 or 4 times. And that's something that will be obvious in a future formal charge video. So this nitrogen bonded 3 times with 1 lone pair. You'll hopefully remember, and as I said, we'll probably have a video all about this coming in the next couple of days, that the electron domain geometry for this nitrogen that I was just showing you is in fact tetrahedral, but the molecular geometry is something a little bit different. Turns out when that lone pair is present, you would say that the geometry of that nitrogen is trigonal pyramidal, would be the geometry you'd assign to that. So there is an electron domain geometry that's based on the fact there are 4 different groups of electrons kind of doing something around there. So it still has the 109.5 degree bond angle, but one of those things is, instead of being an atom, is a lone pair of electrons. And that's something called, or that leads to something called the trigonal pyramidal geometry. And as I said, we'll talk about that in a future lecture, probably the next set of lectures. Okay, so other things that we should kind of recognize about this structure. Let's take a look at oxygen next. Oxygen, on the other hand, you'll notice there's an oxygen and there's an oxygen. And what you'll notice is that oxygen bonds 2 times when it doesn't have a formal charge. As I said, sometimes those lone pairs of electrons are shown, sometimes they're not, but an oxygen without a formal charge is always going to have 2 pairs of electrons that are just kind of hanging out on it. So let's actually keep track of that. So there we can see that oxygen is in fact satisfying its full octet. And just like before, let's pick on this oxygen out here, right here. That guy is bonded to 2 different atoms, and then 2 of the other electron clouds, or lone pairs of electrons. Turns out that once again is based on a tetrahedral geometry, and a tetrahedral electron domain geometry, but we would now say that the molecular geometry of this thing is in fact bent. So you would say it is bent. And so even though it's not displayed in this picture, keep in mind that when we see an organic structure, quite often there's a lot more going on than what is just plainly in front of our eyes. And so even though this thing is super ugly, that I just drew, is that there is actually a bend in this line, right? There's a 109.5 degree bond angle, these bonds right here. Okay. Okay, this, if we want a geometry for that oxygen, well, there's no real molecular geometry for that guy because it only has one other bond to it. But in terms of an electron domain geometry, you would definitely call that thing trigonal planar, just like we kind of saw before. So we're going to add oxygen to our list here, and then I'll just mention a couple other things about this structure, and then we'll go on our merry way. So we see here that oxygen bonds 2 times, but one thing I wanted to just kind of highlight is that once you kind of know the bonding preferences of different atoms, anytime that you find something that's in the same family like this sulfur, you notice that it tends also to bond 2 times. There's kind of a strange thing that happens with those third period elements that they can actually expand their octet. So sulfur can actually bond a whole bunch of different times, more than 4 in fact, but its most likely state is this kind of divalent state where it's bonded to 2 different atoms. One other thing I wanted to mention to you all is that you'll notice that there's a couple of kind of oddball things out here. One of those is this R group. When you see an R group, that's something that is just a general organic group. So in other words, something that contains carbons or maybe not even containing carbons. It could be a chlorine group, things like that. R is just something that represents a whole bunch of other stuff. So what's typically done is you'll see something that says R equals blah, 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 and I'll list off the various groups that R could be. So don't get too bent out of shape about that one. The other thing which I wanted to mention to you all is that you'll notice that there are no like apparent carbons in this structure. And that's because chemists start to get pretty lazy because the fact is that everything in organic chemistry is made up of a whole bunch of carbons. So you indicate carbons just by like bends in chains, right? So here we can kind of see this guy. That is a carbon right there. And of course that nitrogen is projected out at us. And the other thing which you'll notice is if you count up the number of bonds to that carbon, there's only 3. But we know for a fact that carbon has to bond 4 times. It turns out that you very, very rarely show a hydrogen bonded to a carbon in this thing called the skeletal structure. So the fact that the nitrogen is coming out at us, we know that that hydrogen must in fact be projected behind the drawing here. Let me see if I can draw that a little more. So that is supposed to be showing that the hydrogen is projecting behind the plane. If I couldn't figure out how to do a dash without all kinds of crazy things going on. So all that is an open pi wedge right there. There are, of course, other carbons in this thing which aren't shown. Turns out that there's a carbon right there, there's a carbon right there, there's a carbon right there. Basically, anywhere you see the end of a line or you see kind of a bend in the line, there's actually a carbon present there. So let's just kind of go through and label all the different carbons that are there. And of course, you kind of have to keep in mind that if you see something that's only bonded once, like this guy out here, that means that there's 3 different hydrogens attached. This is something called a skeletal structure. And these skeletal structures are something that we'll kind of introduce gradually. You'll start to see them more and more often as we start to talk about functional groups and stuff like that. Okay, so that is the end of the video for today.